We have learned that a propeller generates thrust by accelerating a mass of air rearwards. Unfortunately, a rotating propeller will also create significant yawing, rolling and pitching moments. These moments give rise to 4 turning effects, which must be anticipated and compensated for by the pilot. The majority of piston engines fitted to single-engine light aircraft rotate clockwise when viewed from the rear. This is called a right-hand propeller. The first turning effect we will look at is torque reaction. Because the propeller is rotated clockwise by the engine, an equal and opposite reaction, called torque, will give the aircraft a left rolling moment. During the takeoff roll, the left rolling moment will apply a greater download to the left wheel. The increased rolling resistance from the left wheel will give the aircraft a left yawing moment. You must compensate for the left turning effect from propeller torque by applying right rudder in anticipation. At low airspeed and takeoff thrust, the left turning effect from torque is very noticeable. In flight, propeller torque will generate a left rolling moment, but this can be compensated for by using aileron trim. The second propeller turning effect we'll look at is spiral slipstream. Because the propeller rotates clockwise when viewed from the rear, the mass of air it accelerates will also rotate clockwise. The rotating mass of air meets the fin at an angle from the left, which produces a left yawing moment. In flight, the designers compensate for this by fitting a fixed trim tab to the rudder. But during the takeoff roll, at low airspeed and takeoff thrust, the left turning effect from spiral slipstream is very noticeable and must be compensated for by the pilot using right rudder. The third propeller turning effect is the gyroscopic effect. You have learned in other subject areas that one of the properties of a rotating mass is precession. If a force is applied to the circumference of a rotating mass, the reaction to that force will act at 90 degrees in the direction of rotation. A propeller is a rotating mass, so it too has the property of precession. Let's pitch the aircraft nose up. This will incline the propeller disc. A forward force has been applied to the bottom of the propeller disc. Precession causes the reaction to act at 90 degrees in the direction of rotation, forwards on the left edge of the propeller disc. This will generate an aircraft right yawing moment. The gyroscopic effect of pitching the aircraft nose up is a right yawing moment. If you pitch the aircraft nose down, a forward force has been applied to the top of the propeller disc. Precession again causes the reaction to act at 90 degrees in the direction of rotation, but this time it is forwards on the right edge of the propeller disc. A left aircraft yawing moment will be generated. The gyroscopic effect of pitching the aircraft nose down is a left yawing moment. Now yaw the aircraft to the left. A forward force has been applied on the right side of the propeller disc. As before, precession will cause the reaction to act at 90 degrees in the direction of rotation, but now it is acting forwards on the bottom of the propeller disc. A nose-up pitching moment will be generated. The gyroscopic effect of yawing the aircraft to the left is a nose-up pitching moment. Now yaw right. A forward force has been applied on the left side of the propeller disc. Precession causes the reaction to act at 90 degrees in the direction of rotation, but now it is acting forwards on the top of the propeller disc. a nose-down pitching moment will be generated. The gyroscopic effect of yawing the aircraft to the right is a nose-down pitching moment. Rolling the aircraft does not give a gyroscopic effect because the propeller disc is not being inclined. At low indicated airspeed, the propeller shaft will be angled upwards from the direction of flight. Because of the upwards inclination of the propeller shaft, the downgoing blade will also be travelling slightly forwards. Consequently, the angle at which the relative airflow approaches the blade will be slightly modified. The downgoing blade has an increased angle of attack and will therefore generate more thrust. The effect on the upgoing blade will be the opposite. The upgoing blade will be travelling slightly backwards. Consequently, the angle at which the relative airflow approaches the blade will also be slightly modified. The upgoing blade has a smaller angle of attack and will therefore generate less thrust. If we view a single-engine aircraft from above, we can see the result of asymmetric blade effect. More thrust on the side of the downgoing blade, less thrust on the side of the upgoing blade. Therefore, the thrust line is displaced slightly to the right of the propeller shaft, which generates a left yawing moment. Of the four turning effects we've looked at, the gyroscopic effect has perhaps the smallest influence on a single-engine light aircraft, because of its transitory nature. The other three turning effects, torque, spiral slipstream, and asymmetric blade effect, all cause a left yawing moment. As mentioned previously, their influence on the aircraft will be greatest at low indicated airspeed and high angles of attack. We will now consider the significant influence that asymmetric blade effect can have on the safe operation of a light twin-engine aircraft following an engine failure. Both engines are rotating clockwise. As we saw previously, the downgoing blade generates more thrust than the upgoing blade. The thrust line from the right engine acts to the right of the propeller shaft. The propeller on the left engine also generates more thrust on the side with the downgoing blade, and its thrust line is also displaced to the right of the propeller shaft. If the left engine fails, the thrust from the right engine is acting through a longer arm to the CG and generates a large yawing moment to the left. But if the right engine fails, the thrust from the left engine is acting through a shorter arm to the CG and generates a smaller yawing moment to the right. So if the left engine fails, the pilot must use the rudder to compensate for a larger yawing moment than if the right engine fails. In this case, the left engine is called the critical engine. The critical engine is the engine the failure of which will generate the largest yawing moment. The majority of light twin-engine aircraft do not have a critical engine, because they are fitted with engines which rotate in opposite directions. The left engine rotates clockwise, and the right engine rotates anti-clockwise. The length of both thrust arms is therefore the same, so the yawing moments are the same. As mentioned previously, propellers that rotate in opposite directions on separate shafts are called counter-rotating. This brings us to the end of our study of propellers.